Imagine being able to predict exactly what comes next. Pretty powerful, right? And this is what is at the heart of the decoder-only transformer architectures. And this is also the architecture that powers the most well-known large language models that we know to date, which are models like ChatGPT, the LLaMA models, Qwen, or even DeepSeek. Decoder-only models are excellent at next token prediction and creative generation. And this is because of the pre-training method known as next token prediction, where the model is trained to predict the next tokens based on previous tokens. A very simple example of this pre-training could be to use this sentence. I am creating a video where we can essentially split this sentence into 5 different training samples and train the model on this. So what should it predict when the input is just the beginning of sentence token? That should be I. What should it predict when the input is beginning of sentence tokens and I? That is am, and so on. This pre-training process allows the model to learn certain patterns or ideas or even subtle nuances of language. But really, to be able to pre-train these well-known large language models like ChatGPT or LLaMA, you would need millions or even billions of sentences for this to be possible, because these models contain sometimes more than 400 billion tunable parameters. Now, the decoder is not the only transformer architecture there is. We actually started with the encoder-decoder model as introduced in the paper Attention is All You Need. And basically all other transformer models, they are descendants of this architecture. Now let's take a look at the decoder, as that is the topic of this video. The decoder takes as input a prompt. That could be just a question. Then what it does is that it reads the sentence from left to right in the first masked multi-head attention layer. And this is very important for the decoder, as this is what actually allows the model to do next token prediction by reading only the sentence from left to right. Then in the next attention layer, that is a standard multi-head attention layer, so that allows for left to right and right to left. Then it is just fed into this neural network, and it also has some addition and normalization, which I'll get into. So let's see how that works. So it reads from left to right, from right to left, and then it predicts the first token. So the output probabilities, that is just a list of probabilities where there is a probability for each token in the entire vocabulary. And then it just randomly picks the token based on probabilities. And that is 2008. So let's continue and see if it can predict the correct answer. So it predicts the next token, which is just a comma. Predicts the next because financial. And then finally, we're ready to predict the last token, brothers. And that's it. So the interesting thing about the decoder is that the knowledge is stored in the parameters, right? We just asked it a question and it was able to answer the question based on the weights in the model that we tune with backpropagation like you would any regular neural network. Okay, so now let's focus on some of the essential math of this transformer architecture. Now, the first thing that I want to do is explain this arrow right here, like what happens in this add and normalization layer. And it's actually quite simple. You add the input before it enters the attention layer, and you add that with the output of the attention layer, and then you do layer normalization. And the same thing for the next attention layers, and the same thing for the feed-forward neural network. It's really that simple. The essential math that I want to focus on is in the attention layers, and it is this attention formula that you use. What first happens is that the input is put into word embeddings. So that means that each word in the sentence is being represented by a vector of the model dimension. That is then stored in a matrix with these word embeddings as rows. And there might be n words in the sequence that you give to the model. So that's how that part works. And then there is some positional encoding that just slightly changes these values based on the position of the words in the sequence. And I'm not going to focus on that part, as that is not essential to understand how the decoder works. The attention layers are much more interesting, as that is what really makes the difference. So notice the three matrices in the attention formula: queries, keys, and values. And these we have to calculate. The queries, keys, and values, they each have a weight matrix. So that is a weight matrix of dimension d model by, if it's the weight matrix for the queries matrix, that is then d model by dq. And for the keys matrix, that is d model by dk, and so on. Now, what do we do with the input that consists of word embeddings? Well, we need to calculate the queries, keys, and the values, and they are each represented by vectors. And these vectors you calculate by multiplying the word embedding vector with the entire weight matrix, and then you get the first query. And then you do that with all the words in your word embedding matrix. The first thing we do is that we have to multiply the queries and the keys together. What we get is that we get the attention scores, and they explain how much each query and key correlate to each other. And remember, the queries and the keys vectors, they represent different tokens. So we get an understanding of how much a query of one word correlates with a key of another word. So then what we do after we've multiplied the queries and keys together is that we get what we call the attention scores. And then we use the softmax on this. We also divide by the square root of dk dimension just for numerical stability. Now, using the softmax makes each row in the matrix sum to 1, so that we can see which query and which key correlate the most with each other. Queries and keys that correlate with each other will have high values, and queries and keys that don't correlate, they will have low values. That greatly helps the model understand the connections between the words in the sentence, which will help it predict the next token. So basically, after the softmax, each element represents how much attention is put on the key based on a given query. And this matrix we call the attention weights. Finally, we multiply these attention weights with the values matrix. And it's just basic matrix multiplication, right? So the values matrix is just some weighting that further weights these values that came from the attention weights. And that's it. Now, what happens in the masked multi-head attention? Because it is slightly different. So in the attention layer that I just explained, the query from the first word, we still get a value of how that correlates with the key from a word that came after it. But this is actually not allowed when we try to do next token prediction. So therefore, in the masked multi-head attention, we have to preserve the autoregressive property, which is where the model reads the sentence from left to right. What happens after that doesn't matter. We just have to apply this effect for us to be able to do next token prediction. So what we do in the attention scores is that we remove any influence from future tokens by setting the values to negative infinity. And this makes the model read the sentence just from left to right. What happens when we then apply the softmax to these matrices that contain negative infinity values? Well, the softmax will just take these values and replace them with 0. So up until this point, we've only been talking about attention, but not multi-head attention. And basically what multi-head attention is that the weight matrices for the queries, keys, and values, instead of there being only one matrix for each of them, there are now, for example, 8 different weight matrices for each queries, keys, and values matrix. So basically 8 different smaller brains that each focus on some part of the sentence. And why do it this way? Well, it's just been proved to generalize better. So we just calculate attention as we would with just one weight matrix, but instead we do it 8 different times for each of the queries, keys, and values matrices. Then we concatenate the heads, which is the same as just placing the matrices next to each other from left to right. And then we multiply with some output weights, WO, with dimensions d model by d model, right? Because h multiplied by dv equals 512 in this example. Then we've calculated multi-head attention, and these smaller weight matrices can all be calculated in parallel. And the reason you do 8 different ones and not just keep it as one very large matrix is because this allows the model to learn different patterns. If it was just one very large matrix, then it would still only just try to learn one pattern. At least that's the idea. So I hope you now have a much better understanding about attention and the architecture of the transformer. If you have any questions, feel free to leave a comment in the comment section, and I hope to see you in my next video.